Hey everyone, Mr. Smith here. In this video lesson, we are going to review Newton's laws of motion and types of forces. Hopefully you find most of this review from your grade 11 course. Let's get started. So when we start talking about forces and the forces that cause motion, we're talking about dynamics. So this is a study of forces and effects they have on velocities of objects. Dynamics has origins from the Greek word dynamis, which means power. And in your grade 11 course, you guys learned three important ideas related to dynamics, and we call them Newton's laws of motion. So let's talk about Newton's first law. So just as a bit of a thought experiment, I think everybody can relate to a problem like this. So imagine you're driving on the highway and you're in the passenger seat. So you may be on your phone, listen to music, have your eyes closed. And then all of a sudden, the driver has to hit the brakes really hard. Maybe there's some traffic ahead. So what do you experience as the passenger? So think about that for a moment. And then also think about what if instead, maybe you hit that traffic jam and you were fully stopped. And then again, maybe you're off in your own little world on your phone or what have you. And the driver realizes that the traffic is moving again and they missed it and somebody's honking behind them. They step on the gas really hard and accelerated quickly. What would you experience as a passenger? I'm sure we've all experienced these feelings. So of course, for the first scenario, when the driver hits the brakes really hard, you move forward. Hopefully you have your seatbelt on and prevents you from getting injured. But yeah, you move forward in your chair. And, if the car is fully stopped and the driver hits the gas, then you're kind of put back in your seat. Or maybe if your head was down, your head snaps back up or something. This is the same thing that happens if you're fully stopped and somebody hits you from behind. Your kind of head would snap back and your body is restrained. And this is what we call whiplash. So these ideas are kind of consequences of Newton's first law of motion. If the net force acting on an object is zero, that object maintains its state of rest or constant velocity. So in the first example, if you're just sitting in the car in the passenger seat and it's driving along, the car is moving at a constant velocity, and the driver hits the brakes. Well, the brakes apply a force to the car, not to you. So you would like to maintain your state of constant velocity moving forward. Hence, the car slows down and you continue to move forward out of your seat. Of course, your seatbelt friction applies a force to you eventually as well. But in that meantime, you do move forward. And in the final scenario, if you're at rest, the driver hits the gas, the wheels hit the road apply a force on the car to make it move forward. But you want to stay at rest. And so that's why you kind of resist that motion. So as the car moves forward, you're staying at rest and it feels like you're moving backwards. This law has some important implications. So the first is that you need an external net force required to change an object's velocity. So like we all know, if you're on like a sailboat, like you can't just like blow into the sail to, make the boat work. You can't just like hook up an electronic fan to a sail and make a sailboat, right? You can't, push on the dashboard of a car to make your car go faster. To cause a change in velocity or acceleration, you have to have an external force, and it has to be not zero. Newton's first law, we sometimes refer to that as the law of inertia. So you guys in your grade 11 course would have learned this idea of inertia. It's the property of matter that causes an object to resist changes in its motion. And objects with more mass have more inertia. Objects with smaller masses don't have as much inertia. But yes, all objects with mass have inertia. They resist changes to its motion. And a pretty easy demonstration you can do, as long as you have some kind of card and a coin. is to place the card on top of a finger and place a coin on top of the card. So here I have a Pokemon card. So this is Chimchar. And I've just got a coin. I got a quarter here. Has a bit of substance to it. Didn't choose a dime. Didn't think a dime would work that well. So here I'm just balancing the card on top of my hand, and then I'm putting the coin on top of the card. And I'm going to give the card a good flick just with my fingers, just from behind. And so try it on your own or observe. Maybe even saw this demonstration before. But if I flick the coin, it wasn't perfect. But the coin kind of stays still, right? Let me try this again. Bounce out on a finger. I think I had it touching more than one finger, so there's a bit of extra friction there. Plus, it's kind of hot. Skin is kind of sticky. So let's try this again. Coins on there. Yeah, that was better. But yeah, the coin just ends up staying on your finger. If you weren't all sweaty and things were sticking together. But the coin has inertia, and it wants to, when we flick the card, the coin is connected to the card, but it was resisting that change in motion. I'm only flicking the card. The coin just has inertia, wants to resist that change of motion, wants to stand still. And you might have seen people with a full tablecloth, with like a fully prepared table, plates, cutlery, etc. And they whip out that tablecloth, but all the cutlery and stuff stays there. That's an example of inertia as well. That would have taken a long time to set up. So here I have my coin and card. Let's keep moving. So we're going to do a few examples, not too crazy for our first two, that illustrate Newton's first law. And we're going to draw a free body diagram for each and just talk about types of forces as we go. So first things first is, like, everybody has their own kind of style for drawing a free body diagram. And like some might be more detailed than others, but none is like more right than the other one. So you draw your free body diagrams the way that you feel comfortable. If you want to draw your passenger jet aircraft as a jet, or as a box, or just a point, you do whatever you feel comfortable with. I often use a box, but yeah, you could use whatever you like. If you're a good drawer, draw a passenger jet. So we have a jet traveling with a certain mass, traveling at a constant velocity. We're given that velocity as well, maintaining a constant altitude. And we're asked to find the net force acting on the aircraft. So first of all, let's draw the forces we have going on here. So hopefully the most obvious one, we have an aircraft flying through the air. And the first force we have acting on it is a gravitational force pulling it down. So you would have referred to that as, in your grade 11 course, as weight. And the way we calculate gravitational force is we do the object's mass times acceleration due to gravity, g. So that's hopefully review for all of you. We probably should also talk just like the units of force. You guys learned in your grade 11 course is the Newton. This is the standard unit of force. There are many units of force, but the standard one we use is the Newton. We use the symbol N. You guys have learned this, refer to this as weight. And maybe this is the first time in your life when you took your grade 11 course that you actually stopped saying weight and mass to mean the same thing. So mass is mass. It's like I weigh, or there, I caught myself. I might have a mass of 80 kilograms, let's say. But weight is a force. Weight refers to the gravitational force on an object. So if you say, I weigh 80 kilograms, that's kind of a misconception. Your weight is the force that gravity exerts on you. And the units of weight, I'm not going to bother erasing those. The units of weight, since weight is a force, is the Newton as well. So please keep that in mind. So what else do we have going on here? Well, the jets is maintaining a constant altitude. So there must be some force acting up as well. Otherwise, the plane would crash to the ground. And so here you can call whatever you like. I might just call it F and then maybe lift. Now the aircraft has to move forward somehow. So maybe if my aircraft is flying to the right here, I might call this an applied force. Now we don't have somebody pushing the aircraft through the sky, but the aircraft is probably expelling some kind of, or burning some fuel and expelling some of that backwards to propel it forward, or maybe it has propellers and is pushing air backwards so that it moves forward. And we'll talk about Newton's third law later, but some kind of applied force propelling it forward. Now this jet is not. If this was the only force acting on the jet in the kind of the horizontal direction, then the jet would just keep accelerating forever. But we're told it's traveling at a constant velocity of 850 kilometers per hour. So we know obviously that there is air resistance. There it's not flying through the vacuum. So let me just call that F air. And so that's how I would draw my free body diagrams. Just a simple object, draw all the forces going on. Later on, when we solve problems, it'll be useful for us to assign directions to be positive. So that can be done with something as simple as like that. Up is positive, right is positive. And that's just kind of a simple free body diagram. Now let's answer the question. What is the net force acting on the aircraft? And if you want to reread Newton's first law to answer that question, you can. But since it's moving at a constant velocity, there's no acceleration. There's no external net force. So the net force acting on the aircraft, say F net, is 0 newtons. So it's almost a bit of a trick question. But because it's moving at a constant velocity, Newton's first law says net force acting on an object is 0. That object maintains a state of rest or constant velocity. So if our plane is at a constant velocity, the net force acting on it must be 0. But that was a good exercise in drawing a free body diagram. If you have your own style, hey, that's great. That's kind of my style. Okay, so the second example. So say that you exert a force of 45 newtons up on your backpack, and it causes it to move upwards with a constant velocity. What's the force of gravity on the pack? So let's draw a free body diagram for this one. This is a pretty simple one. Here's my backpack. Gravity, of course pulling it down. Fg equals mg. And we are applying a force up. So I might draw that. Might call it F applied. And we know that it's 45 newtons. And that's all we have really going on in this question. And so I might assign a direction up to be positive. Let's determine the force of gravity on the backpack. Well, the key term in this question here is that, again, it's moving with a constant velocity. So what do we know from that? We know that F net has to be equal to 0. And if that's the case, then the size of the applied force has to equal the size of the gravitational force. That's the only way that we can have 0 net force. Those things must be perfectly balanced. And so that must be 45 newtons. The force of gravity on the pack is 45 newtons. If you prefer to say Fg equals 45 newtons down, you could say that. But I think we all understand if we say the size of the gravity force equals 45 newtons, we understand that straight down. Now, personally, if I was doing a question like this, and you might see that later as we do more examples in tomorrow's lessons, I might just eventually say, Fg equals 45 newtons. This is the size of the gravitational force, and we understand that it acts down. But again, coming from different classes, you just do what you feel comfortable doing. Let's look at a third example. Now this one, admittedly, is a bit more involved, and we're going to be using components. So here we have a traction system. So maybe you've been in one like these. I've never been. Maybe you know somebody has. But if somebody damages a leg pretty severely, they've got to stabilize the leg so it doesn't move. And so they use something like this called a traction system. And so they kind of hang the leg up and they attach it to this pulley. And the pulley is attached to, or these multiple pulleys are kind of attached to the ceiling via a string or some kind of rope, fairly strong rope. And the rope would have some kind of mass hanging at the bottom to provide some tension. Some things to note: this tension, and you guys will learn this in your grade 11 course, this is the same string in this entire pulley system. And that means the tension in that string is the same all the way through the string, everywhere. So the tension where it's at the mass, the tension pulling away from the pulley in the downward direction, in the upward direction, the tension is always going to be the same. While we're talking about that, let's just actually talk about what is that tension. Well, if we have this weight providing the tension that has a weight of 18 newtons, well, we think back to the last example, what must the tension in the string be? Well, if the tension in the string, or if the system is in equilibrium, so the forces are balanced and it's not moving or moving at a constant velocity, then these must be balanced. And the force of tension, so you can use Ft, or you can maybe just maybe you like to use a capital T, whatever you did in your grade 11 course is fine, is 18 newtons as well. So we know that the tension everywhere in the string is 18 newtons. So let's draw a free body diagram. I'm going to draw one very lightly, just kind of loose. And then I'm going to bring up a graphic of a much better one, detailed with angles and stuff that you can copy down and we can use for our solution. So if we think about the forces acting on the foot right at point P, we have a tension pulling the leg up, like so. And you can call that Ft. I like calling it Ft. We have, and if you want to call it Ft1, that's okay too. Sometimes that might be useful to differentiate between the tensions, but I hope you understand after our last discussion that the tensions are the same. And we have the tension acting at a different angle too down here. I might throw those angles in. That's 57 degrees, and that's 32 degrees. Here's a second tension force. Of course, its magnitude, its size is also equal to, it's the same size. So what I actually might do, just calling an audible here, I'm actually just going to not even mention these are the same, because these two tensions have the same size, but they are in different directions. So I am kind of reluctant to say they're the same tension, the same magnitude of tension. They're both 18 newtons. And we have the force of the leg on the pulley. So remember, this is just a free body diagram for the pulley, right? It's not a free body diagram for the leg. So we can assume this pulley is very small and actually has really negligible mass. And so what we have is a third force. And it may look like it from the diagram, but the leg isn't horizontal. That leg actually has to be kind of hanging up in the air to be stabilized. And so the leg is probably pulling down in some downwards direction, like so. And I might just call it F leg, or if you want to call it F tibia. I think the diagram I have in a second calls it F tibia. We'll see in a second. And our kind of goal is to figure out what that force is on the pulley. What's the size of the force, and what's the angle of the force too? So let me pull up here just a lot more detailed free body diagram. Oh, the horror. I'm going to erase that. So I'm going to erase the work I have here. I thought it would come up over top. That's okay. Easy fix. Just erase all this stuff. One of the downsides of shooting several video lessons per day is that you don't really have the time, if things don't go perfectly, just to reshoot the whole thing. Or at least I don't, with 2 kids and a dog. So we'll just do this. And yeah, here's a detailed free body diagram. So we have the size of this tension being 18 newtons at an angle of 57 degrees, the size of this tension being 18 newtons. And we have the tibia force kind of pulling it down to the left. And as you can see, it'll be helpful for us to analyze this problem in terms of components. If we can break these two tension forces into components, we could figure out what the x direction force has to be to balance them out. Remember, the pulley is not moving, it's in equilibrium. It's in equilibrium because there's no acceleration. And so we can find that x value. And if we can find the sum of these two tension forces, their vertical components, we can determine what the necessary y component is for the tibia force as well. So at this point here, it's pretty much a problem we've solved several times already, breaking things down into components, recombining into a single vector. So let's get started. So we're gonna break things down horizontally. Lots of ways to illustrate this, but for my tension force acting up, I'm gonna call that Ft1, and the angle there is 57 degrees. So again, you can choose to do this however you'd like, but I'm just giving a suggestion here. So I'm gonna call this Ft1x and Ft1y. And so I can use trigonometry to get those values pretty quickly and efficiently. And again, we've done lots of these examples, so I feel like we can move like the tiniest bit faster through these. So Ft1x is going to be 18 newtons, the size of Ft1, times the cosine of 57 degrees because it's adjacent, and Ft1y, I keep putting the t there. I like using t for tension sometimes too, but then later on, t is going to refer to something else when we get to uniform circular motion. So I think we'll just keep it as Ft1y is equal to 18 sine 57 degrees. And these are just magnitudes. And I think I've kind of mixed up my horizontally and vertically here. So I think that's okay. I think I'm just going to go with it. It's fine. I'll let you know how we can structure it a bit differently in a moment or two. But let's just actually calculate these guys. So Ft1x is 18 cos 57. So that's about 9.8 newtons. And Ft1y, 18 sine 57. That's about 15.1 newtons. And let me draw the second force as well. So the second tension force is kind of going down, Ft2. Its angle with the horizontal was 32 degrees. So we'll break that down into Ft2x, T2x, and Ft2y. Again, not the only way to label these. It is a way, and you can structure it differently if that's just the way you like to roll. But the size of that tension force was also 18, and the x would be cosine 32 here, and Ft2y equal 18 times sine of 32. Cos 32. So we get about 15.3 newtons for that. 18 sine 32, about 9.5 newtons for that. So now I might say, okay, so let's look at horizontally. So what does F tibia x have to be equal to? Well, if this whole system is in equilibrium, then the size of that x component of the tibia force has to perfectly balance out the sum of the two x components of these tension forces on the other side. So that F tibia x has to equal, in this case, Ft1x plus Ft2x, And again, this is just one way to kind of get this down and reason it out. So we have 9.8 plus 15.3. So the size of that tibia force in the x direction, 9.8 plus 15.3, I think that's 25.1. This is my third video today on top of hanging out with my kids. So I'm going to check on a calculator. 25.1 newtons in the x direction. That's great. And then vertically, I'll just tuck this down here. So vertically, F tibia y So let's check this out. So let's be careful here. So F tibia y is acting down. And we've chosen down to be positive in our case here. And so we will take FT2, that's in the positive direction, and we will subtract FT1y, which is in the negative y direction. So it'll look something like this. F, keep doing the t's. Guys, I think I'll take a break after shooting this video. My brain's getting fried. FT2y, and we will subtract FT1y because we know that's going in the opposite direction. So we have will we do that? FT1y. I see. So we just have to be careful here. So because the tibia force is downwards, the sum of the two tension forces to balance it out must be upwards. So when I do the subtraction, my hesitation was that I was getting a negative number, but that's okay. So we have 9.5 minus 15.1. Minus 15.1. We get negative 5.6. But the key idea is that it's 5.6 newtons downwards. So we can put these two things together, and we'll do that in our next slide as well. So we have summary. We got the force of the tibia on the pulley, and we just found these components that for there to be no net force, the x component must be 25.1. And the y component must be 5.6. And that wasn't the only way to get those values. It wasn't the only way to structure it, but it was a way. And so we are almost ready to go. We've got to this point many times before. So the size of that tibia force will be the root of 5.6 squared plus 25.1 squared. And the angle of that tibia force will be using tan, and it'll be the opposite, 5.6 divided by the adjacent, 25.1. So let's get those two values and wrap up the problem. So 5.6 squared plus 25.1 squared. Don't forget the square root. About 25.7 newtons. And the angle, 5.6 divided by 25.1, inverse tan, about 13 degrees. So we can conclude F tibia equals 25.7 newtons, and it's 13 degrees below the horizontal. To the left, I should say. So yeah, a little summary there. So we made a free body diagram and we illustrated those components. We broke the two tension forces into components, and I kept everything in terms of magnitudes. So if we wanted to talk about combining those two tensions, and I said just FTY, we have 15.1 newtons, and it would be up plus the 9.5 newtons going down. And so if we write that as negative 9.5 newtons up, then what we get is 5.6 newtons up, which means that the F tibia in the y direction has to balance that, and we get 5.6 newtons down. So that's another way to kind of illustrate that. I think in hindsight, I got the right magnitude there, but I think maybe an alternate way to illustrate that might have been better. That's okay. That's what happens when you try new stuff. But I think both ways we can easily see, it has to be 5.6 down to balance things out. All right, so that was a bit of a more involved example, Newton's first law. That's our most involved example for today. The last two are pretty quick. So we now talked about Newton's first law at length. Newton's first law involves situations where the net force on an object is zero. So there's no acceleration occurs. And again, that could mean it's at rest, not moving at all, or it could mean it's moving at a constant velocity. His second law includes situations where the net force is non-zero, where you have some net force causing some acceleration. That acceleration is in the direction of the force. And you would have spent some time in your grade 11 course verifying this is true. But if you have some external net force on an object that's not zero, the object one will accelerate in the direction of that force, and the acceleration is directly proportional to the net force and inversely proportional to the object's mass. Now that is a fancy way of saying what you're probably more familiar with as Newton's second law is basically F equals ma. The sum of forces, i.e. the net force, equals mass times acceleration. This is net force. So again, it is a sum of multiple forces. It's equal to mass, a scalar, times the acceleration, a vector. Now, Newton's second law, as it's stated here, looks kind of like this. The acceleration is proportional to the net force and inversely proportional to the mass. And if you kind of turn that into an equation and rearrange it, multiplying up the m, you do get sum of forces equals mass times acceleration. That's Newton's second law. Thought I had an example for you guys. I do have an example for you guys on your lesson sheet, but I don't think I put it into the lesson. That's okay. We can do this. That's right here. You know what? We're going to keep our notations. We're going to do a little fix on the fly here, guys. So we've done Newton's second law. I'm going to duplicate this slide and clear this stuff out. Get over that. And I think I have the lesson sheet here. I do. There's our example. And I want that in here. So I'm going to insert, screenshot. Yeah, this will work. Let's get that in there. Slideshow from current slide. There we go. Nice. Yeah, full disclosure, there's no way I'm restarting this video. I've already sunk a good 20 minutes into it. Easy fix. Let's keep moving here. So we got a hot air balloon, and its total mass, including the passengers, is 900 kilograms. We have a gravitational force. We have the weight of the balloon. It's 8,800 newtons downwards. And we're given a buoyant force that's keeping the balloon in the air or causing it to accelerate upwards of 9,900 newtons. We're going to find the acceleration of the balloon. So let's draw a free body diagram. So we have our gravitational force, and I might just write Fg in this case. We're given that that is equal to 8.8 times 10 to the 3, which is 8,800 newtons. And we're also given the buoyant force. So maybe you want to call that FB, can be flexible. And for this particular problem, I might just do things a bit differently. And I might just drop the vector signs and understand that what I'm writing out now are the magnitudes here. 9,900 up. And I'm going to add a sign convention. I think here it makes sense for up to be positive. All right. We also understand that our acceleration will be up as well because that buoyant force is larger than the gravitational force. But what is that acceleration? So there are many ways to set up Newton's second law, many different notations, and as many of there are of you, which is right now about 35 in my class, you might have had 25 or 30 different teachers. So there's going to be lots of different ways of doing things. So I'll show you how I prefer to set these up when I'm applying Newton's second law. So I will start with sum of forces equals mass times acceleration. I'm not too worried about the vector signs right now. I understand that this is, these are vectors. But with things going on in one dimension, I'm okay with just starting that, everything's in the one dimension here. Sum of force equals mass and acceleration. And what are my forces that are being added up? Well, I have my buoyant force, which I have in the positive direction. So I'll put positive FB. And I have gravity acting in the opposite direction I've chosen as positive. So I like to throw that in as minus Fg. So my sign convention here takes care of its direction. Equals mass times acceleration. And we know that gravitational force, the weight, is equal to m times g. But you know what though? We're actually given that gravitational force. So I don't even need to do that. So I don't even need to rewrite this next line. I'm actually ready to solve for my acceleration right away. That's great. So what I prefer to do with these problems is I prefer to rearrange for what I'm solving for, which is A, and then plug in. So A equals FB minus FG over M. And now I'll plug in. I do this because if I wanted to vary some of the parameters in the problem, I wouldn't have to resolve the problem. I would just go back to this point here, my formula for A, and I can just replug in. So we have 9,900 minus 8,800, all divided by the mass, which is 900 kilograms. And let's just do that. So we get, I think that's 1,100 on top. Yep, divided by 9.8. So we get about 112. Definitely not 112. I divided by 9.8. Guys, I'm losing it. I think I've reached my upper limit on videos I can shoot per day before I start to mentally break down. 1,100 divided by 900, 1.2. I was thinking 100 meters per second squared for a hot air balloon is incredibly fast. That's like 10 Gs. Those people would probably not survive. And the units we know would be meters per second squared because we have newtons divided by kilograms. All right, now, if I may, just offer you maybe a second way of setting this up. So for some of you, you may prefer to actually just, maybe this is the way you've done it before. You might write FB and keep all the vector signs plus FG equals mass times acceleration. And you might just keep everything kind of do the same thing I did, but you might just keep all your vector signs divided by the mass. and then maybe you plug in, but maybe you keep the directions. So you might be saying 9,900 up plus 8,800, don't need that there, down, all divided by 900. And you can see we get the same solution because that's negative 8,800 up. And so you get 1,100 up divided by 900. And you get the same answer. You get 1.2 meters per second, and it would be up. And the way I set it up, by choosing my direction to be positive, I understand if I got a positive answer for A, 1.2 meters per second squared, I know my acceleration is upwards. So I would consider both of these, equally good. You should just stick to what you're comfortable with. And this is generally what I'm comfortable with. So yeah, 1.2 meters per second squared. So we kind of found the net force by doing FB minus FG, and then divided by M. Right, let's move on to Newton's third law. So a classic example of this is, and I'm sure everybody's done this before. When you inflate a balloon, but instead of tying off the balloon, you just let it go. What happens to the balloon? Well, of course, it flies all around the room. And you might ask, well, if it's flying around the room, something must be providing some kind of net force on that. And as the balloon expels the air, so the balloon itself, the surface of the balloon on the inside is pushing that air out. The air is exerting a force on the balloon as well, causing it to move around. We have this kind of action-reaction pair. This is Newton's third law. Now, Newton's third law actually considers forces that act on a pair of objects, whereas Newton's first and second law have to do with a single object when the net force is 0, and then Newton's second law, where there is some external net force. Newton's third law involves pairs of objects. It says this: for every reaction force, there is a simultaneous reaction force, equal in magnitude but opposite in direction. So here's some examples. So this third law is often called the action-reaction law, and it explains situations where a force is exerted on one object by another. So here's some examples of some action-reaction forces. So for a tire on the road, the tire, and if the car is moving this way and the tire is turning, the tire exerts a force on the road. This might be called the action force. And what causes the car to move forward is that the road actually exerts an equal and opposite reaction force on the tire, causing the tire to move. The road is fairly secure in place, so the road is not going to move backward. It will stand relatively, it'll stay still. But we've all seen, on loose road, that we might have some loose gravel kind of spinning back outwards, and we can kind of see that example of the force of the tire on the road. How do we walk? How do we run? Well, we exert a force on the floor, and the floor exerts a force back on us, an action-reaction force. This explains how we can row in a boat. So if we want to move this way, we exert a force of the oar on the water, and the water exerts a force back on the oar. And since the oar is connected to us, connected to the boat, it can actually move the boat. So those are just 3 examples. Here's just one last example. Can you think about what the action-reaction pair in this example is? If you have a player sliding into third base and kind of slowing down, coming to a stop. So you don't have to write anything down almost. You just want to just think about this one and have a discussion. You can pause the video and unpause when you're ready to see, but I'm just going to reveal the solution right now. So in this question, it doesn't matter which you choose to be the action force. Here you can say the action force, it's the force of the ground on the player. So the ground is exerting a frictional force on the player. And given this choice, the reaction force is the force that the player exerts on the ground. And that's something you can kind of see, because for relatively loose dirt, the player is lying on the ground, you can observe the kind of pebbles on the ground maybe moving along with the player. Conversely, if we call the action force the player exerting a force on the ground, the reaction force is that friction force, the ground on the player slowing it down. So we are going to make use of all three of these laws as we move forward and look at some more involved 2D dynamic scenarios. Now, depending on your course last year, maybe you looked a little bit at inclined planes, and we all talked about friction. So we'll talk more about friction next day too. You've maybe talked about pulleys, etc., a combination of all. But we're going to look at more involved scenarios, might be using component method a little bit, but it should be pretty fun. And then that will wrap up our first unit on motion and dynamics in 2 dimensions. So guys, hope you're staying well. Thanks a lot for your patience during that lesson with a few technical difficulties. Hope you guys have a great day, and we'll see you soon.